So today we saw how to interpolate images, and then today we will use it. So yesterday we already introduced a recording with enlarging or shortening an image. So what we this interpolation is useful when you do geometrical transformation. But geometrical transformation is this kind of operations where you have some input image and then you distort the space so that you have the image in a different region. So you can see the original region was much shorter than this one. So, and for that you will need any coordinate here where it goes here. So we saw it yesterday with a zoom. So we introduce it in this way. So we say, let's say that we have using some nice colors for that. So let's say that we have an input image, some object, and then you have a location here that we will call R, and then we transform it into a different one that is, let's say, smaller. So it is a smaller one. Then you have to say R prime, this pixel is coming from this one. So what you need is a transformation. So say R prime is transformation of R, and then R is the inverse of that transformation applied to R prime. Okay, so this transformation, if it goes in one direction, if it goes in this direction, it is T. If it goes in the opposite direction, it is T minus 1. So yesterday it was just a scaling factor, and today we will make it more general. So let's say this is explaining what I said, and this is also called geometric remapping. So there is a transformation that goes from one space to the other. So let's say that we have this image, and this image, see that the powers, they seem to be like of tilted, and in reality they cannot be like that. So they have to be straight towers. So it is a problem of the camera and the perspective. So let's see how we can distort that. So you need to find some correspondences. So you need to find a few points, like in this one. So you need to know this point goes to here, this point goes to here. So you need to define a few pairs of points. And then from those pairs, you will estimate the function. So let's say that we define all these points. These numbers are the coordinates. And then we say, these points, so these points should go to here. So you may see, for instance, this one. Sorry. So you see, this point will stay fixed. So it doesn't move. So it has the same coordinate. And this one, this is y. The y will be the same, but the x will move. So the x will, the x, I want it to be at 52. That is the base of the tower. So it is the same x as the base of the tower. Then the y has to stay the same. And the same happens for all the others. So for instance, this one, the y stays the same, but the x goes to the base of the tower. So it goes here. The x goes to the base of the tower. Okay, so we are just changing x, but not changing y. So in general, you will have p pairs, and you will have correspondences. So this will be in one of the spaces. This one will be in the other space. So J is in which space? So J is the output, I is the input. And then you will transform from J to I. So the way it is defined, it is H minus 1, H minus 1, when you go from H to I. So it is this transformation. So the transformation we have chosen. So in general, this transformation can be whatever. So it can be any transformation. It's one. But we have chosen one that is one matrix of multiplication. So HR, but we do HR, and H is a matrix, and this is H minus 1 R prime. Okay, so this is what we have. This is R prime multiplied by H minus 1, and then you have the point where you have to interpolate. Now you interpolate at that location. Okay, so then how to solve for H? So this we already solved. So let's say that we have, I will do it, I think this notation will be more clear. So let's keep it here. So let's say that we have pairs of, so I have R prime 1, that is mapped onto R1. I write this way. And then I have R2 prime, that is mapped on R2. All the way to RP prime, that is mapped to RP. Okay, so these are 2D vectors. So that is a 2D vector, a 2D vector, a 2D vector. So the size of this matrix, this is a matrix that is of size 2 times P. It's 2 times P. This is a 2 times 2 matrix. And this is a 2 times P matrix. So how many unknowns do we have? So this is an equation system, isn't it? So it is an equation system. How many unknowns do we have? These two are known. So this is our unknowns. So we have only 4 unknowns. We have 4 unknowns here. How many equations? So we have 4 unknowns. How many equations do we have? For every x and y, we have an equation. So we have 2p equations. So in general, you will have more equations than unknowns. As long as you have more than 2 points, you will have more equations than unknowns. Then you know that we cannot solve these in an exact way. So you have to approximate, because in general, there will not be any solution. So H is the argument that minimizes with respect to H. Is the sum over all points on P of the norm of. So we are going from R prime I minus H Ri squared. So what we are saying is, okay, I know that H will not satisfy exactly all the pairs. So I will take, so H is mapping from R to R prime. So I will take every point in R, map it to R prime using H. There will be a difference. And then I will compute the norm of that difference. And then I will add all those norms and try to make them as small as possible. And we call this problem the least squares solution. Squares solution. We already reasoned how to compute that. So so we say, okay, so I will rewrite this in this way. So this is an R prime matrix. Okay, R prime This is H times R. Okay, so R points go through H and they are mapped to Y or to R prime. Then what I would like to do is something like R prime, R minus 1, R. Okay, so this is what we would like to do, but we cannot do that because this matrix is not a square. We cannot do that. So we have to somehow do this with quotes. So what are the quotes? So, okay, so let's study the sizes of these things. So let's go back again. So we have R prime is H R, and we said this is 2 times B. This is 2 times 2. This is 2 times B. So let's multiply by on the right by R transpose. By multiplying on the right by R transpose. What I have. So this is 2 times B. This is B times 2. This is 2 times 2. This is 2 times 3. This is B times 2. So this matrix is 2 times 3. And this matrix is 42 times 2. So now I can multiply on the right by the inverse. Unless there is any problem with the determinant of that matrix that normally you will not have. So I can multiply by the inverse of that matrix. So I can have R prime R transpose times R transpose minus 1 equal H. And then this is within quotes. This is my inverse. Remember, so it is R prime times something. This is the something I'm looking for. So this thing here is called the pseudo inverse. Pseudo. But it's not an inverse because the inverse of R is not defined. But it is as it is an inverse. So this is called the pseudo inverse. So now we have H. So that is what we have here. So the notation is different. It's using X and Y, but I think it is more clear R and R prime. And now you have it. So now you have your H. So you take every coordinate in R, you go to R prime, or if you want to go the other direction, you want to go as we did yesterday. Yesterday, we were going from the output to the input. Then you use H minus 1, but H is a matrix, so you can invert it. So you take every point in the output, look where it is coming from in the input, and then you interpolate there. So this is this equation here. So you take every point in the input, in the output, multiply by H minus 1, and then interpolate. And this is just the rounding. So this is rounding. Okay, so we have our points. So we calculate H. This is H. This is H minus 1. Do you remember it was a change in X? Okay, so let me write the matrix here. You remember Y was staying fixed, and so H only H minus 1 is 0.97, 0.202, 0.1. So that means that we are taking X prime, Y prime. So R is equal to this matrix. 1, x prime, y prime, property is this is x, y. So this is 0.97 x prime plus 0.02 y. So y doesn't change. That was we were keeping y all the time the same, and we were only changing x a little bit. So here we have the little bit. So it's changing a little bit, and then you change it more or less depending on where you are. If you are closer to the base, you have to change less. If you are upper in the tower, then you have to change more. Okay, so makes perfect sense with respect to what we know. Okay, then we apply, and this is what we have. So it is a little bit better. So this is where we start. This is where we want to be. And this is our transformation. So it is a little bit better. It is a little bit better, but not exactly as it should. So we wanted to go from the tilted tower to the straight tower. We have improved a bit, and but not quite. And now we see these squares. So these squares means we cannot fully satisfy all the conditions. This is the best we can do, and the error is not zero. Okay, so then let's see if we can do better. And for that, before doing that, we will introduce a notation that is called transformation. That is this one. So any matrix you can decompose in this way. Do you remember the eigenvalue decomposition in algebra? Algebra, you had something called eigenvalue decomposition, and it was you have any matrix. Let's make it here. So you have any matrix, A, and you can decompose. That's B minus 1. And this was a full matrix, this was a diagonal matrix, and this is the inverse of this one. And this diagonal was made of values. And this P was made of some vectors. 1, 2. And it was these values and these vectors, they were such that when you take one of these values, vectors, you get the same vector, but multiplied by something. And this was called the value of this were called the eigenvectors. Valore proprio. So instead of this one, this is only defined for square matrices. And for any arbitrary matrix, so this is only defined for n times n matrices. We have an arbitrary matrix, any size, then this doesn't exist. But there is another decomposition that is this U minus V transpose. That is called this singular value decomposition. Singular value decomposition. The spirit is more or less the same. So this would be an m times m matrix. This would be m times n. This one would be m times n. So the spirit is the same. Not exactly this property, but quite similar to this property. And it is defined for any matrix. So now you do the singular value decomposition of that matrix. And final is 3 matrices. So if you multiply the 3, you have the same age. But now there is a property. So look at these 2 matrices. So this is a rotation matrix. So have you seen rotation matrices? So a rotation matrix is one. A rotation matrix is one. Can be written in this form: cosine of an angle, sine of an angle, minus sine of that angle, cosine. Yeah. When we have any vector here, and you multiply by r, what you are doing is you're turning this so this point is r. Okay, so it is a rotation. Just take any vector you rotate by an angle theta. Okay, so this is cosine, sine, minus sine, cosine. This is a rotation matrix, and this is also a rotation matrix, and it is not by chance. So any transformation, and this is a scaling matrix. This is the kind of zoomings and scale changes that we were doing yesterday. So any transformation can be decomposed as first a rotation, then a scaling, and then a rotation back. So let us see. So yeah. So first the rotation. So the first rotate, then you scale, and then you rotate back. And any transformation can be decomposed in that way. Okay, so why we didn't succeed? Because so we made it better, but not as good as we wanted. So this tower is not as straight as we wanted. And the problem is that this transformation is because you have a 3D object, that is this building, and you're projecting it into a 2D image. So the transformation you have defined goes from 2D to 2D. So you have to find something that goes from 3D to 2D. Okay, so that will bring us to introduce something that I call homogeneous coordinates. So these homogeneous coordinates is you will define an homogeneous coordinate. So let's say. So you will have an homogeneous coordinate R. So to avoid confusions. So then we put this tilde on top to say this homogeneous. So this will be a vector x, y, k. And this vector is represented, so it is a 3D vector. So this is a 3D vector. And it is representing a point that is x divided by k, y divided by k. So you see there is not a unique way of representing a point. So let's say that I have the point r is equal, I don't know, 1, 2. So there are many vectors of this kind fitted. So one of them is 1, 2, 1. This is one of them. But also this vector R2 that is 2, 4, 2 is also that one. And also this vector -1, -2, -1 is also representing the same point. So given a point, you can represent them. You can represent it in many different ways. All of them represent the same point. And that representation will be called the homogeneous coordinates. Okay, so now let's put our problem in homogeneous coordinates. So you are giving me some coordinates in one space, in one image. I will make them homogeneous. I will multiply by a matrix that is now 3 times 3 because we have 3 dimensional vectors, and then that will give me another 3-dimensional point that is the homogeneous coordinate of the point I want to represent. Okay, so it is simply going 1 dimension more. And instead of working in 2 dimensions, I will work in 3 dimensions. But now I have 9 degrees of freedom. So before we had only 4 degrees of freedom. So in our least square problem, we only had it was here. I don't know where we were counting. Yeah, here. So we only had 4 degrees of freedom, only 4 parameters to play with. But now I will have the same problem, but now I will have 9 degrees of freedom. So now I have 9 parameters to try to make the coordinates match. Okay, so let's do that. So we have our coordinates in one space, we have the coordinates in the other space. We don't know the case yet, okay, but there will be some case, and we will get rid of the case later. So you take coordinates from one space, you multiply by h, then you have the coordinates in the second space. So this was input multiplied by h, and then you have the coordinates in the output. And then, okay, so let's rewrite this equation system, but now as an equation system instead of matrices. Okay, so we have it here. So this is the equation system that is coming from this one. So it is exactly this one, but I have expanded it and written as an equation system. Okay, and now you do something that is divide the first equation by the last equation, and the second equation by the third equation. So you divide, this is what we get. And then we will fix something. So because of these many representations that we saw here, you can imagine that this freedom that we have here, this freedom of choosing case, and choose many different case that gives infinite solutions. So let's try to fix these infinite solutions that have only one solution. And the way to do that is to make this H33 to fix it. So we will fix it to 1. So we fix it to 1, and we keep on doing. Okay, so now you rearrange, take this part from the denominator, you move it to the numerator, same here. This is now the new equation system. And now, which are our unknowns, the H, so the matrix, the parameters of the H matrix. So you take the H as an unknown, and now you rewrite this again as a matrix. Okay, so you will have. So let's do it. I don't know how to do it so that I don't get lost copying. Do you need that I do it in the whiteboard? Do you get the idea? Or do you know how to go from here to there? No? I will explain that. So you take, so H will be H11, H12, H13. Okay, so now let's rewrite this equation. This will be H11 minus Xi, H12 minus Yi, H13 minus 1, H21 is not here, so you have 0. H22 you have 0, and so on. Okay. So when you multiply this row by this column, you get this equation. Okay. And the same down. Now, so for every pair, so these are the coordinates in the input, U and V are the coordinates in the output. So, and you have xi going to ui, so xyi going to uvi. So you do that, so every pair is giving you two equations as before. And now we have A times H. If you look at on the other side, we always have 0. This transform one equal. Yeah. Because it is a kind of convenient way for the one is not an unknown. It is a convenient way of taking each one. This U and V multiply by 1 and then you get this one. Yeah, but you are right. This part could be considered the independent term. When you write AX equal B, this would be the B. Okay, so, but if you move it to the other side, then you put here 1, and then you have the equation AH equals 0. Okay, so how to solve for that? We will use SVD. So use SVD again. So this matrix is now is A matrix, we know. And then the way to look for H is you do the SVD decomposition. And the SVD decomposition, you have that diagonal values, so some values in the diagonal. You look for the minimum value in those p values. So which one is the smallest of this one? And the smallest, so let's say that the smallest is the second one. So the second one will have an associated p vector in this decomposition. So the H that we are looking for is P2. So that is some anti-RAM tool to solve this kind of equation systems. So when you have AH equals 0, then you can solve it in this way. Okay, and now, so I have the B. So I have the B. So that is my H. That is my H. Now you have the matrix that transforms points from the output to the input. And you have to use H minus 1 because H was going in the other direction. But so it is the same as before, but only that now we have 9 parameters instead of 4 parameters. So we can do a better transformation. Yeah. And you are predicting, because this is a 3 times 3 matrix. So this is the homogeneous coordinate. And you don't have homogeneous coordinates in images, you have normal images. But once you have your homogeneous K, you simply have to divide by that to have the correct input location. So this is simply undoing the homogeneous transformation. So yeah, that is in general. We don't have the result with this one. May try also with MATLAB. We don't have this in. Okay, then rotations. So rotations is the same as we have in general, it is all the time the same. So you have some transformation that goes from one coordinate space to the other coordinate space. So you have one coordinate here, you transform it into something else. If this H is a rotation matrix, now we have introduced rotation matrices below. So if this is a rotation matrix, then it will rotate it. That's it. And then it's getting too detailed in, so this thing. What is the sizes of the input, of the output if I rotate? There are regions that are not defined. So let's say that I have this input image, I rotate it. So, and you keep it on the same frame. So there are regions in the output frame that are not coming from anywhere. So this point here is not coming from anywhere in the rotated in the original image. At this point here, it is the same. Okay, so when you rotate, either you keep it in a bigger image, and then still there will be points that are not defined, or there are corners that are not defined. But there will be points that are not defined. And he's getting too detailed on which are these points that are not defined. Actually, I don't care. So this is this idea. So when you rotate, either you keep it into a bigger image, and still there will be all these areas that are not defined. Or if you keep it in the original frame, still there will be areas that are not defined. So, and he's getting too detailed there, so I don't care about this. Okay, so then, so let's, we have this image, and then you rotate it, and then you can, we saw yesterday different interpolation schemes. So you can do it in cubic, in its neighbor, linear, and you know the how it goes. This is the most accurate, this is the second most accurate, and this is the least accurate. So when you compute differences, what is the most accurate interpolation minus the least accurate one? And these are the pixels where they differ. And then you see, mostly they are at the edges, as they should. So if some region is very flat, doesn't matter which interpolation you use. All kind of comparisons, bilinear versus cubic, so all kind of comparisons. But also, you can have very interesting transformations. So, for instance, this one. This one is let's think of something. So there are some cameras. Some cameras. In which, let's say that you want to have a kind of 360 degrees camera. So you put it in a spherical mirror, and then you are seeing the whole thing with this spherical mirror. So how can we do that mathematically? So this is. So you will have an output image, that is this one. You have to look from for every point in the output where it is coming from in the input. So we can do that this way. So you will define, so the output image will be of some size. So we will define this rho parameter. Okay. Then you take every coordinate in the output, add out the out. Then you compute raw. This is just a polar coordinate. So these two make a polar coordinate. See? And then you compute this thing, this phi. Okay? And this phi is using something that depends on where you are and how large is your image. Okay, now for the input image, compute the 0. And then you make the following calculation. So you compute D using D0 and this phi parameter that we computed. And then once you have D, you undo the polar transformation. So now you have a very nice way of going from the spherical image to the Cartesian image, to the square image. So you make some you compute some parameter for the output, and then for every point in the input, you compute some parameters, and then you use those parameters to go to the location in the square image, and then you have to interpolate there, and this would be the result. So it is a way of mathematically simulating how you would see the images in these spherical cameras when you only have a square image. But the idea is the same. You have some geometrical transformation that transforms points from one space to the other, no matter how complicated is that transformation. So it can be as simple as a matrix multiplication, or it can be as complex as these spherical mirrors. But as long as you have a way to go from coordinates to coordinates, you apply that transformation and then you interpolate, and you have the value of the image at that location. That's it. The last one. So, any question?